Welcome to the deep dive. Our mission today is to take the spec sheet for a single piece of industrial hardware and really turn it into some essential insights. We are looking at the NTI E-PST200IS pressure sensor transmitter. Now, if you look at the source material, the first thing that jumps right off the page is the price tag, $2,600.
Yep.
That is not impulse buy territory. So our goal is to unpack this. What exactly makes this device worth that kind of money? And what does this term intrinsically safe actually mean for you, the user, who might be working in a really high-risk environment?
What's fascinating here is that the specification answers the why almost immediately. It's designed to monitor pressures in explosive atmospheres. We're talking about critical infrastructure, think refineries, chemical plants, maybe even grain silos. These are places rated as hazardous areas, Class 1, Division 1. The entire point of its design is, well, to prevent a catastrophe.
That brings us right to the core concept here, intrinsic safety. We often hear about explosion-proof equipment, which I always figured was just, a really tough metal box designed to contain an explosion if one happens inside. But intrinsically safe.
Right. Yeah.
That's different, right? How does this sensor do it? Does it just have better seals or something?
It's a completely different philosophy. I mean, totally different. Intrinsically safe means the equipment is engineered so it can't ignite the atmosphere in the first place.
Yeah, okay.
It does that by severely limiting the electrical energy. The whole idea is, if you can't make a spark or generate enough heat to hit the ignition point of the gas around it, you simply can't cause an explosion. It's a low-energy design, which is actually much harder to engineer than just, bolting a thick case around something.
Okay, here's where the cost gets really interesting for me. If the sensor itself is designed to be spark-free, why does the source material say that to use it in these hazardous locations, you absolutely need an EISZB intrinsically safe barrier, which is listed separately for another $810? Doesn't the sensor already handle the safety?
That barrier is non-negotiable. It has to be there because the sensor is only one half of the equation. The barrier sits outside the dangerous area, and it basically acts as a choke point for the electricity. It guarantees that no matter what happens on the safe side, say a power surge from the grid or a short circuit in the control room, the power that gets through to the sensor inside that explosive zone is instantly clamped below a safe level.
So the barrier is the gatekeeper for the power.
Exactly. It manages the fault tolerance for the entire system.
So on top of that $810 barrier, the sensor also needs the ES420MA24V to work with certain controllers. For anyone not familiar with industrial controls, what does that string of numbers tell us about how this thing fits into a bigger system?
It tells us two really key things. First, the 420MA part. That's the signaling standard. It's like the bedrock language of industrial control. The sensor sends its pressure data by changing electrical current. It's super robust and resistant to noise.
Okay, so it's a common language.
Very. And second, it confirms this isn't some standalone gadget. It's built to plug into a very specific monitoring ecosystem, those E2D, 5D, and 16D controllers you mentioned. You're buying into a whole vetted system.
And if we look at the physical limits, the safety design dictates some surprising rules. The source notes a maximum cable length of 1,000 feet or 305 meters. Why such a specific hard stop for a piece of wire?
That limit links directly back to keeping that intrinsic safety rating. See, over a long distance, the cable itself starts to act like a capacitor and an inductor. It can actually store electrical energy.
Oh, wow.
Yeah. So even if the barrier is doing its job, if the cable stores up enough energy, a simple break or a fault in the wire could release a spark.
And that would defeat the entire purpose.
The entire purpose. That 1,000-foot limit is the engineered maximum to keep that stored energy safely below the ignition point.
Even the connection is hyper-specific. 18-inch BNPT, male 316 stainless steel. That's a lot of acronyms for what looks like a simple pipe fitting.
Well, the material is key. 316 stainless steel has superior corrosion resistance, which you need in chemical plants. But the BNPT threading, that's a British pipe taper, it's designed to mechanically lock and seal as you tighten it, and it makes sure no process fluid can leak out.
So it's protecting against the very thing it's trying to monitor.
Every single detail serves that one safety mission.
And finally, just as a nod to the kind of money we're talking about, the source mentions a 2-year warranty and a free 15-day trial. This is clearly a high-stakes investment. So when you put it all together, what does this all mean? I think this NTI sensor shows that in these really dangerous environments, monitoring pressure isn't just about getting a measurement, it's about paying a massive premium for engineered, provable risk mitigation.
It is. The sensor is a tool, but the ecosystem around it is the guarantee. And when you look at the whole picture, the sensor itself is only one part of the cost. I think the real insight is that cost breakdown. A mandatory $810 safety barrier is needed to protect the $2,600 sensor. That means almost a third of your cost is just for fault protection. It really makes you think about that entire unseen ecosystem. How many other essential, dedicated, and expensive safety components underpin the reliability and, the actual safety of the world around us?